So the one thing I have to figure out after the tomorrow's sessions is how you guys saved it to the WebEx, the recording. You said you didn't do anything. It just saved it there.
Yeah. So, so we can make it available to the teachers after the fact. I just now clicked record.
Well, I understand how to do the recording, but when I was done, it would say, where do you want to save it?
I don't recall getting that option. It just went to WebEx. It appeared on my WebEx recordings.
Interesting.
That must be the default.
Okay. That's good to know.
Well, we'll wait a couple more minutes and we can get started. We want to remind everybody to go down and click the chat bubble. We're going to have you put your questions in chat rather than Q&A so that Bill and I can both see them. If you'll select send to all participants or all
panelists.
All panelists, not participants. We don't want too much chaos, do we? Should we go ahead and get started, Bill?
I think it's time, David.
Okay. So, welcome to all of you. It's a pleasure to have you in attendance at this session for seventh graders, seventh grade teachers, ultimately seventh graders at some point, if we ever get to see them in our classrooms. I'm going to, first of all, I just want to, in addition to welcome you, say how much I appreciate, how much we all appreciate the the effort that you put in to making your classroom work during these difficult times. A lot of us don't know what the next fall semester will bring, if it'll be different in November than it is in September, and we'll just have to learn as we go. It's certainly not a comfortable position for many. So keep up the good work, and we really appreciate it. We're here to help you. If there's anything we can do in the future, do please feel free to contact any of us. So that said, let's go ahead and get started. I'm Dave Cederberg. I'm the Outreach Coordinator for the Department of Physics and Astronomy at Purdue, and I'm one of five in our group. And today we're going to talk about balloon rockets, and I'm going to start with a PowerPoint to highlight some things that I want to make sure I don't forget. So I'm going to share that with you now. Let me do that. And okay, so I do want to say that some of the materials that we are providing for the teachers who subscribed and paid for the initial our initial group who subscribed and paid for the workshop. Some of those materials are provided by an NSF career grant And when I say career grant, I mean a grant from one of the faculty. In fact, it was Professor Birgit Kaufman who funded some of the materials that we are providing for you. So let's, I'll explain to you before I get started. I tend to cough a little bit. I don't have COVID, and it's just an irritation that I have that comes and goes. And right now it's coming instead of going, but I'll try and do my best. We're going to start with just a review of Newton's laws of motion. I don't think it's important that students know which law is first and which law is third. What's important is that they know the concepts. So one law, we can call it the first law, is it, and I guess literally the laws build on each other, but in any case, the first law is what I would call the body's at rest law. And whether the body is at rest or actually in motion, it's in a steady state. So it could be at rest, it could be in constant motion. In either case, it will stay in that state until acted upon by an outside force. Simple as that. The second law, the proportional to force law, things happen, there are actions and there are reactions. And if something happens to a force acts upon a body, whether it's at rest or in motion, the result is proportional to that initial force. So if a body is in motion and you give it a boost, let's think about a child on a swing. The swing is moving, you give it an extra boost, it will accelerate, and that's directly proportional to the force. And then the action-reaction law, which is like, if there is, it's the equal and opposite idea. There is an action on something, and then there's a corresponding reaction. So, we're talking about balloons here. So here's a balloon. It's in equilibrium. There's air inside. It's not going anywhere unless I let go. And if I let go, the air coming out will propel the balloon in the opposite direction. So there's a force that the air is coming out, that exerts a force in the opposite direction, and we have a resulting reaction. I'm not sure I explained these very well, but there are plenty of resources on the web to fill in the gaps. So, mention a couple things that we played around with this lab for several weeks. Professor Kaufman and I started with some ideas, and she experimented and collected some data, and then I worked with a couple of students earlier this spring, and we all had fun. And I think excuse me, I think your students will have fun too. So how much space do you need? How long a string? I think it's going to depend on your room, on your own situation. Try something and see what works. We tried large balloons, 12-inch balloons. We also tried smaller balloons. These are 9-inch. The smaller ones seem to work a little better, but how big the balloons are and how much you inflate them are purely just going to depend on how much space you have. So try it and see what works for you. We tried different balloon pumps, and some were better than others. This one seemed to, the one that we provided to some of you, seemed to work pretty well. These are about $7 a piece. They are, I think, a decent pump, and they're, I think, pump a little more air than some that we saw. So on the subject of pumps, so one of the things you're going to want to collect data-wise would be how much air is in the balloon. The depth to which you go into that with your students is going to depend on your own situation. Do you want them to measure? In the instructional video, I showed how to draw a line on the balloon and mark the cross and measure the circumference. And from that, you can calculate the diameter and then the volume of air. That's a lot of algebra. If that's beyond what your students can do, you don't need to do that. In fact, if you're going to graph something that depends on how much air is in the balloon, that could be circumference, period. It could be number of pumps on the balloon. So you can adapt the data that is collected to your own situation and to the ability of your students. One of the things that we discovered, we probably should have not had to discover this, we should have known in advance, but when you stretch the string and you hook the hook around a support and you have the straw and you put the balloon on the straw, where do you start? Well, we decided it would be a good idea to visually put a piece of tape on the string so the students could be consistent and start at the same place every time. We started with using a Sharpie and putting a mark on it. That didn't work because it was invisible. It was too hard to see. But a piece of tape, the size of your thumb, would work well to mark the beginning, the starting point, as well as if there's an ending point where that would be. Another thing that I think is a thing to keep in mind, when students do this, they sometimes fidget too much with the clip, the baggy clamp. Have them squeeze the neck of the balloon, take the clamp off, and then release from there, rather than release by just taking the clamp off, because that will not work very well. So I'm just going to put that back on there for now. And I think it works well to have students assigned roles. If your students are doing multiple trials, and they will, you want them to be consistent. And if one student releases the balloon one time and another student another time, if one student pumps one time and another student pumps the other time, it's not going to be very consistent. So I would assign roles. You have a pumper, you have a launcher, someone who'll record the time, and someone to write down or record the data. And I have some other tips about those jobs a little later on. And I would always have my students do this a few times to try it, so they can see how the balloon reacts. They can find out if they're recording time with a stopwatch, if they're accurate enough, if they're consistent. And so, a few practice runs, I think, would always be a good thing. I want to tell you, if you have any questions during this time, please type them into the chat window, and Bill will stop me and let me know that you have a question. And I guess if we did, Bill would let me know now. So I'm going to go to the next slide. We're going to talk about two experiments. One is the distance of motion. It just means you're going to down the string, you're going to make a starting point, pump the balloon up to a volume, and then measure where it stops. So the volume will change and the distance will change. I will tell you that we tried to devise an experiment where we could measure the velocity, how fast the balloon might go based on the amount of air in it. And we found out that didn't work very well for a couple of reasons. The primary reason is the nozzle, or the outlet on the balloon, is a constant size, and whether the balloon has a lot of air or a little air, the amount of air coming out of the nozzle is essentially a function of the size of the nozzle, not how much air is in the balloon. So, and I've got some data to show you this a little later. It didn't work very well. So we decided a better approach for the first experiment would be not how fast the balloon goes, but how far it goes. And so you've done this, you've seen the instructions and probably have done this. You're going to use different volumes, measure the distance, and graph that data. and I'll show you some data here in a minute. You could do velocity. You will do velocity. You could also measure, I'm sorry, we don't ask you to do velocity. We ask you to do distance. You could, however, do velocity. It would be average velocity, and you could do that with a stopwatch and the distance. Here's some data from experiment 1. We graphed both. We graphed this data 2 different ways. If the students have the mathematical capability to do some calculations, for example, from their circumference get diameter, and from diameter calculate the volume. If that's important to you, I think those are good skills. Once they do it, once they do it the first time, it's easier to repeat that those calculations, and they're going to do it 5 or 6 times. However, if you're going to graph this data, it could be the circumference, it could be the volume, gee whiz, it could be just the diameter or just the number of pump strokes. So we graphed this, I think, a couple different ways, but I'm showing you all the data we collected. I would also say, some of our data is in the English system and some is in the metric system. That's your call. If you want to do it inches, fine. I have no feeling or no opinion about that. I'll leave that up to you. So from that first experiment, we graphed distance versus circumference. And you see what looks like a trend, a pattern. I don't know if it's if it's a straight line or a curve, but it does show a definite pattern. We took the same data and graphed distance and pump strokes, and we have the same pattern. So I just want to show you the comparison. It doesn't matter which one you graph, the trend will be the same. And I mentioned we played around with larger balloons. We wanted to do velocity versus the volume of the balloon. And when we started to experiment with how we might best do this, and what activities would be most beneficial for this grade level, as I said, we wanted to do volume versus velocity. And I'm not a rocket scientist. It would seem to me that the more volume, the more air would come out the nozzle and the faster it would go. And that definitely was not the case for a couple reasons. I mentioned the size of the nozzle, but look at this graph. We have average velocity versus the volume of the balloon. And this is certainly the exact opposite of the trend I would expect. As the volume of the balloon goes up, the average velocity goes down. So it's an okay experiment. It would be fine to do this with your students because I think it would be somewhat of a discrepant event, which is always a good point to start learning. So you might have them do it and then try and explain why. Here's one of the things that I think enters into this, and that is when we did this experiment, we used a 12-inch balloon. So that's going to be, about twice the diameter of this one. And the large balloons, number one, they're heavier. And number two, they have more air resistance. And so when the balloon is fully inflated and you let go, there's more friction with the air, more air resist, and it takes it a longer time to build up speed. And by the time it does, it's almost out of air. So there's the experiment, and you can do with it what you will. We did not write this into the lesson. However, you certainly could do it. How about experiment 2? So we scaled down our balloons and we started to use smaller balloons. And I think this one is, as I say, maybe a 9-inch balloon. It's not fully inflated. And we decided to try and add a cargo. So, one of the things about doing balloon rockets is it's a model for how rockets work. And so rockets carry a payload. And rockets have fuel. And the more payload, the more fuel. And so, you have to weigh which one you need. Do you need more payload, or can you get by with less payload and save fuel? In any case, in experiment 2, we have a starting point and we have a fixed ending point. So the distance that the balloon travels will be the same in every trial. The volume that you start with will be the same in every trial. So we've isolated the volume, we've isolated the distance. What we're going to vary is the mass. And so we take the balloon, and you saw the video, I don't need to show you, but we start with, let me just stop for a minute. If you're going to talk about mass, you have the choice. Do you want to include the mass of the balloon? That would be the balloon and the straw. Or do you want to just have the mass of payload, the cargo? Either way is going to be a fine experiment. If you want to be a little more accurate, you could have your students weigh the balloon. You might ask them if it'll weigh the same inflated or not inflated. They may not get that right, but it's an interesting question. And then add different masses. So we're holding the volume, the amount of fuel constant. We're changing the mass. And we're going to look at how, if we look at the time and the distance, we're talking about velocity. So we're going to look at the difference in velocity of the balloon with different cargoes. You could, if you wanted to, if it's within the algebraic capacity of your students, also look at average acceleration, if that's appropriate. If you think about the formula, the equation for acceleration, the distance is 1/2 at squared. A is acceleration and t is time. If you want to solve for acceleration, then we could rearrange that equation and have acceleration is equal to 2s over t squared. Now, physicists call distance, they represent distance with s. I'm not sure I know why. It seems like it should be d to me, but maybe d means diameter or something else. But so whether you use d or s, that's entirely up to you. I think for 7th grade, for middle school grades, D would be fine if you think that makes more sense to your students. And so let's look at some data. I did not calculate the volume. I didn't measure the circumference. Didn't calculate the volume. We went with number of pump strokes. Now, let me back up for a minute and say, if you're going to do this in your classroom, you need to figure out in advance how long a string you need. To do that, I would start with, so, before you do this with your students, you're going to decide what size balloon you'll use and how long a distance you need. Take the balloon, add the maximum weight that you will use with your students. That might be 4 washers. We used washers, pennies are fine. You want something that weighs about 2 to 3 grams. So use the heaviest mass that you will use and run that experiment a few times to see how long a string, you see where it stops. That would, and then back up a little bit. If it stops at 15 feet, well, then I'd maybe use 12 feet. And that would be the distance where I have my starting point and my stopping point. Now, if you take mass away and you have less mass, you're still going to stop and start at the same place, but it'll go faster. And that's the whole point. So here's our data. I'm going to graph the number of pump strokes, or I could graph, let's see, the number of washers. Let's see, I don't want the number of pump strokes. I want the number of washers. Or I could graph the total mass, or the mass of just the washers. I think in this experiment, we used the mass of the balloon and the washers combined. So I could graph, let's just take a look at some graphs. We calculated, or we graphed the mass versus average velocity. So we see as the mass goes up, this is the graph on the left, as the mass of the balloon and washers increases, the average velocity decreases. And we graphed the same data using acceleration. So we graphed the mass of the balloon and acceleration. And you see the graph looks the same. They're both inversely proportional to both variables are inversely proportional to the mass. So why is that? Well, the more mass, the more inertia, the more resistance to change in motion. So if you want the same change in motion with more mass, you would have to have a greater force. So the purpose in this experiment is, well, there are many purposes. Students can learn, they can use some algebra and mathematical skills. They can graph. They can learn, they can enjoy science, and they can learn something about Newton's laws of motion. NASA has, there's a ton of stuff on the internet. I don't need to tell you about Newton's laws. In fact, you could probably find 20 different versions of a balloon rocket experiment. Maybe none are as good as ours, but there are a lot of them out there. NASA has some stuff as well. And here's a link in the PowerPoint. And I will make the PowerPoint available to you, put it in the folder where you got your lesson and instructional materials when we're done. But here's just a diagram from NASA's website showing the action. So we have the balloon on top and a real rocket below. So the action and reaction. The balloon is in equilibrium when it is sitting on the table or held in your hand. No forces are acting on it, at least no propulsive forces. Gravity is certainly acting on it. Air pressure is acting inside and outside, but it's not moving. And if I set it on the table, it will continue to stay there. If I open up the nozzle, then the balloon will take off. And that's the Newton's third law, action and opposite reaction. Analogous to a real rocket. So, and NASA has their own version of this, of the Balloon Rocket Lab as well. I can't believe we haven't had any questions. Did you all fall asleep? No? Okay. Let's talk about some pedagogy. If you think of anything you want to ask, just pipe up. I've already mentioned, mathematical skills and graphing. This is easily adaptable to whatever math skills your students have. I think I also mentioned assigning students roles in their team. Another option would be maybe you're short on time and you don't have time for each student group to go through 5 different trials of each experiment. You could assign specific lab groups a specific trial. So, these 2 lab groups do, if you're thinking about experiment 2, these 2 lab groups do 1 washer. These 2 do 0 washer, no weight. These two, and you get the idea. And then you could compile and combine class data on the projector, and everybody and share, and everybody see that they contribute a part to the overall picture and show the entire graph.
David.
Yeah.
So just a couple comments that were made. People said, there's just a lot to think about. And so you're giving them a lot to think about, which is great. They also said it makes things more in depth, and I'll definitely be adding more to their class. So that's awesome. But then the question was, and I think I know the answer, both, at least what I would do. Where would you put the veneer motion detector? Probably at the end point facing the balloon as it comes towards it, or on the other end where it was coming from?
Well,
Thoughts?
these people are thinking in advance. I haven't even mentioned the motion detector yet, but I do have an answer to the question. If we did this, well, I can't show you the video. I tried to find it this morning, and I don't know what happened to it. But let me show you how I would do this. If you have motion detectors, the balloon may be too small to be picked up by the motion detector. Here's what I would do. I would take a piece of cardstock, or not too heavy, a piece of cardboard. Cardstock works well. I'd find where the center is. I'd poke a hole in it with a pencil and put the balloon through the cardstock. Then I would blow up the balloon. Sometimes when I do that, I get carried away and the balloon pops. Now, here's what I would do.
Hey, David, why don't you make yourself full screen so they can see this?
Okay. That means I have to stop sharing, right?
Correct. There you go.
Just myself. Okay. Am I full screen now? Okay. So I've got the balloon, the nozzle of the balloon sticking through a piece of cardstock. You have the choice. So well, let me just hold this. You're going to have an allowance for where the string goes on top of the balloon, the straw. So you've got the straw, you've got the card. So you're going to need a second hole in the card, or maybe just a smaller card. The problem is that when you let go of the balloon, it's going to get smaller and smaller and further away. So it's just going to be a very short time that it's in view of the motion detector. So I think having a card so it has a little more surface area works well. We did this and it does work well. You have the choice of having the balloon move. If here's my detector, the balloon could move away from the detector, or I could set the detector at the other end and it would move toward the detector. I think you could do it either way. We did it moving away from the detector. I think we got pretty reliable data doing that, although you could certainly try it both ways and see. But that seems to work pretty well. Did I answer the question, Bill?
Yeah, and I'm going to throw my 2 cents in. I would be concerned about putting it on the end where it's going. So if you're looking at David to his right, where the balloon is, because as it starts to shoot that way, the balloon's going to get smaller and smaller. So the detector will detect that, where this other way, the paper's going to not get smaller and smaller. It's going to stay the same size the whole way. Does that make sense?
It makes sense to me.
Yeah.
I will also tell you, I'm going to admit my ineptness. More than once, in doing this with a couple of students this spring, more than once, I got this all set up and realized that that I had the detector on the wrong side, or I had the balloon facing the wrong way. So I know this sounds silly. I had the detector here and the balloon like this. And when I let go of the nozzle, which way is the balloon going to go? Boom, right into the detector. So, it's a silly mistake, but I made it at least twice. You probably will too. So maybe your students can laugh at you the same way mine laughed at me.
The other thing, David, that hold that back up one more time, if you would. I think it would also, and this is going to cause a little bit of problem, but you think about where your string's going to attach onto the balloon, and you don't want that friction on the paper. So you may want to cut a V out in the paper. And I wouldn't want to switch where the paper is because I'm worried about, it actually being able to detect it. And you don't want to put it down lower because then it's going to weigh the balloon down. But if you cut it like a little V where the string goes, then they won't get the friction. Does that make sense?
Yeah.
Yeah. Okay. That's
so,
it.
Another complication with doing this is the paper has a fair amount of air resistance. And so, that will affect your results, but you can talk about that or not talk about that. I'll leave that up to you. That's a good question.
Yeah. The comment was you'd also have to take into account the weight of the paper, which is true. One of those you try a couple times, make sure it works well before you let the kids do it.
Okay, so where were we? I think I went the wrong way. Okay. We used, so I'm going to talk about stopwatches. We used the stopwatch on a mobile phone, which is fine. However, I did this with a grad student assisting me, and multiple times, and I do mean multiple times, we would do a run, and the grad student would hit stop on the app on the mobile phone and miss the button. I mean, it may sound silly, but you got a small button. It's a touch button. You can't tell if you hit it or not until you realize that the stopwatch is still running. So we decided maybe if you have the option of using a mechanical stopwatch, that has a mechanical button, at least a button that sticks out, and you can feel when you press it, and you feel when you release it. We thought that might be an advantage. However, the mobile phone apps work just fine too. You just have to, and maybe your seventh graders are more adept than we big guys are. So, that's entirely possible. Let's see. I like this lab also for the reason that kids can do this at home. So if you happen to be, teaching remotely, balloons and string are easy to come by. And it's not a lot of cost. You could also, if you only see your students twice a week, if you're in kind of a mixed mode of teaching, take some, little baggies and put a kit together, put some string in there and a couple of balloons. And I do encourage you to use balloon pumps if you're going to send a kit home with a kid. Still, I would feel uncomfortable about sharing blowing up balloons. So that's one thing I think I would like to provide would be balloon pump. But a middle school student could easily do this at home with a parent, either providing the materials themselves or if you send a kit home with them. A question that was asked earlier about using the same balloon for the whole experiment. We found that the balloons you know, here's a balloon that's been blown up a few times. Uh, and you've blown up balloons. You know, when you blow up a balloon, when is it most difficult? When you first start. Once you get it going, it's easier to then make it bigger. Second time you blow it up, it's easier. And the third time's easier still. So they do deform somewhat. And but that doesn't seem to be a real problem. So we tried it. We tried using the same balloon with 10 or 12 trials, and we used then a different balloon for every trial. And I think our results were more consistent using the same balloon for 10 or 12 trials, even though the balloon tended to be somewhat, I'll say, deformed. It started a little bigger than it did initially. The problem with using a different balloon for every trial is, number one, you're going to use a lot of balloons. Number two, the balloons aren't all equal. They're not. There are, you know, little differences. We found balloons. You know, there's oftentimes a spot on the end where it's kind of the center spot of the balloon, and sometimes when you blow it up, that stays in the middle, and sometimes it's off to the side, and you know, so there's too much variation, I think, from one balloon to another. In fact, I don't know what this balloon will look like. Oh, so there's a good example. That balloon, the center part of that balloon is off to the side. And so I would not use that balloon. I don't know if you can see that very well, but you can understand. The little dimple is here, and the center of the balloon is more here. And so I would not use that balloon. I would discard it. So use the same balloon for each experiment, and I think you'll be fine. Now, Bill used to teach middle school, and he's done this experiment, and he used, excuse me, he used different kinds of balloons. First of all, you know, if you're going to think about calculating volume from circumference, this is not a sphere. So you have to think about that. Do you want to calculate that, or just as it'll equal itself out? The error will be uniform, and maybe it'll be okay. But Bill tried what I would call cylinder or cigar balloons. You know, a balloon about like this, it's a cylinder. And we didn't try that. However, I think that would be a good thing to try because, number one, the air resistance will be less. And number two, it'll probably be to attach to the string. So you have a cylinder balloon, you could use a whole straw or maybe use two straws, one at each end. And I think that's worth trying. And we've already talked about, excuse me, we've already talked about motion detectors. So I'd like to field any other questions if you have any other questions. Bill, any other questions?
Not that I see of yet, David.
My goodness. Well, I'm going to let go of the PowerPoint and come back to you live here in a minute. I just want to say a special thanks to our professor, Birgit Kaufman, for number one, helping to organize the material for the workshop, for helping to develop this lesson, and certainly for her grant providing the materials for many of you to use. So with that, I will stop sharing, and we can just come back and have conversation.
I'm going to jump in here for a second, just for clarification. When David said that professor provided the materials for the workshop, that professor provided some of the materials that David had for his labs. The materials that were provided for the workshop, for those of you who were able to pay, came from an endowment that we have from an alumni. And the reason I'm saying all this is there was a question asked to me, you know, boy, if you ever do this in the future, I'd like to be a part of the part where I get the materials. we had enough money to buy materials for 60 people. And so that's what we did. And just to make sure that those people had vested interest, they each paid $20 to get the materials, which basically paid for shipping for the most part. And then we shipped them roughly about $100 worth of materials. So that's where the money came from for that. And then David's professor allowed him to buy some materials for his stuff as well. Is that fair to say, David?
Sure, yes. There's a question about assuming uniform acceleration. I think, so if you're going to calculate acceleration in either of these experiments, it would be an average acceleration, which from a theoretical point of view is maybe not very useful or meaningful. It does help students understand the concept of acceleration. And, when students see the units for acceleration, meters per second squared, I don't think there's a middle school student on earth that really knows what that means. I would say there are a lot of high school kids that don't know what that means. There are probably freshmen at Purdue that don't know what that means. But if you break it down and think meters per second, I mean, you can conceptualize speed, meters per second, distance over time. Take that quantity and put it over seconds or over another unit of time. So meters per second. And so that might be, a more tangible way to think about acceleration. So let's just say 5 meters per second. So our acceleration in the first second is 5 meters per second. In the second second, it's 10 meters per second. And in the third second, it's 15 meters per second. So I know there are different ways you can think about this to make it make sense. I think I wouldn't say that either the experiments are uniform acceleration, although I'd have to maybe think about that. Bill, you can chime in if you want to. But I'm thinking of, the experiment 2 with the washers and the masses. I want to tend to say that I don't think the acceleration is uniform because while the mass of the balloon might be constant, the amount of air in it is different and the air resistance is different. And so I don't think it would be uniform. Anybody is welcome to correct me.
And I guess what I'm trying to figure out from the question, so when I taught middle school, I mean, we did acceleration. So we did final velocity minus original velocity divided by time. And with this, the original velocity is 0 because the balloon's just sitting there. And then you would calculate the speed and then so it was those two, and then we would subtract. So I guess to me, I'm kind of going, okay, I don't know if the uniform acceleration, I'll say is important, but if it is, I'm thinking about in a car, if I push the accelerator and I keep it at the same and I keep accelerating again and again, that's uniform acceleration. But if I just push the accelerator down and I hold it at a certain point, eventually I'm going to get to an end point and I'm going to be going at a constant speed. So the balloon takes off and it has a certain amount of force and goes across. At some point you're going to start to have some deceleration due to the balloon slowing back down. And so I don't know. I'm kind of with you, David. To me, I'm trying to think of what my end goal is.
Okay.
Okay, but hold on. But as you said, I think it's a great experiment to talk about accelerations, open up avenues to converse about variable acceleration. Yes, I agree.
We long for the days we can have these workshops again and see you in real time and ask real questions face to face. Although the upside to doing it remotely is some of you are across the country or in a different country, and we wouldn't be able to do this with you otherwise. So it's a good trade-off, but it's unfortunate we can't see all of you and just talk like real people. Anyway.
Any other questions that we have? I want to make sure we have plenty of time for people. If they're going to the next session that starts in 10 minutes, they have time to get there. There's another session at 2 o'clock and another session at 3 o'clock, and they're both the same session, dealing, I believe, with rocks and minerals.
Okay, well, I think we have covered what we need to. I think we could bid you farewell and hopefully see you next time around. Bill, any last comments?
Yep, they said they liked the mass problem. Great presentation. Really like the graphing idea. Appreciate your PowerPoint. And some thank yous. Thank you. So like David said, he'll make that PowerPoint available inside of his presentation materials. So just go back in there and look for it in there. Awesome.
Everybody, thank you very much. Bye-bye.